Okay, so for complex numbers, the key is to be able to write a given expression of the form a plus bi, wherein both a and b are real numbers. Okay, so let's do that one. So for the first item, take note that when we see a bar out here, a line out here, that refers to the conjugate of a complex number. Basically, what you need to do is that you change the real part in the, to be specific, the coefficient of the imaginary part into its corresponding change in sign. So in this case, that would be a minus bi. Okay, so we'll have here, this one is simply just 1 plus I. Okay, so that's straightforward. We just change the negative 1 out here into positive. That's the answer for the first item. So pretty quick. That's just conjugates of complex numbers. Okay, good. So we move on to this next one. So we have square root of -1 minus square root of 3 plus square root of 2 minus negative square root of 4. So this one, just recall that whenever you see a square root of -1, that simply just means I. So that's the value of I. So in this case, we'll have here I minus square root of 3 plus square root of 2. And then for the last one, take note that this one can be viewed as square root of 4 times square root of -1. And then square root of 4 simplifies to 2. Square root of -1 simplifies to I. So we get here plus 2i. Oops, this should be minus. This should be minus since we have here minus. Okay, and then let's just simplify. So again, we combine the real and imaginary parts. So the real part is this one. So we have here, let's just write it nicely. Maybe square root of 2 minus square root of 3. And then for the imaginary part, take note that we can view it as coefficients. So we have here I minus 2i. This will just be 1 minus 2i, right? Or simply just negative I. And so this is the expression in the form a plus bi. Take note that you can be technical about this one. You can write this one as plus -1 times I. But having -1 out here is also fine. Okay, good. So that's for the second one. For the third one, we have here 3i times quantity I squared minus I cubed plus 5i raised to 5. So just like in the usual things in real numbers, we just distribute this term per term. So we'll get here 3i cubed minus 3i raised to 4 plus 15i raised to 5. Oops, this should be 6. And then from here, are we done? Not yet, since again our goal is to segregate the real and imaginary part. But so far we have powers of I out here. So what's the solution with that one? Let's have some certain derivation out here. So let's here, note. Obviously we have here I, which we know to be square root of -1. So that means that I squared must be -1, right? Since if you take the square of this one, the radical sign will just be removed. And then I cube, take note that I cube can be viewed as I times I squared. But I is square root of -1. And I squared is -1. This means we can write this one as negative square root of -1, or simply just -I. Okay, the last one, I raised to 4. Take note that we can write this one as I squared times I squared, wherein I squared is -1. So we have -1 times -1, or simply just 1. So notice that all you need to remember actually in powers of imaginary numbers are I, -1, -I, and then 1. So given those values, you can get any imaginary. Since take note that if we continue this one and we have I raised to 5, this can be viewed as I raised to 4 times I raised to 4 is 1, I is just I. So we get I. And we actually go back in this first one. And you could do the same. I raised to 6, you get this one. I raised to 7, get this one. I raised to 8, this. So basically it's just a loop. I hope you were able to visualize that one. So yeah, so these are only the 4 possible values of imaginary powers of imaginary numbers. So pretty nice. So that means 3i cubed out here can be written as 3 times negative I minus I raised to 4 can be viewed as 1. How about for this last one? Take note that I raised to 6 can be viewed as I raised to 4 times I squared. I raised to 4 is simply just 1, so we can disregard that one. I squared is equal to negative 1. So this last one will just become 15 times negative 1 or minus 15. Okay, good. And then from here, let's just simplify. So we'll have here negative 3 minus 15. Let's combine that one into negative 18. And then this one will become negative 3i. The key here is to not forget this derivation. So remember that with all your heart. That would be beneficial to you as you go along the long math. Yeah. So for this fourth one, we have here quantity 1 plus 2i times quantity 3 minus 4. In here, we just do the usual FOIL. Let's write this one as... So first, multiply this one. So we get 3. The outer, 1 times negative 4i, that's minus 4i. The inner, this one, we get 6i. And then the last, we get 2i. This one. Okay, let's be precise on that one. 2i times negative 4i. That is equal to negative 8. Then I squared is negative 1. So this becomes plus 8. And then let's simplify this one. So we get here 3 plus 8 is simply just 11. Then negative 4i plus 6i is simply just plus 2i. And that's the answer for this problem. Let's go on to the fifth one, which is 2i minus 3 squared. Okay, for this one, just apply the usual again. Square of a binomial. Square this, square that. Multiply this 2 times 2. So for the square of the first one, we have here 2i squared plus 2 times the product of the 2. So we have 2i times negative 3. Then the square of the last one, so that's just negative 3 squared. So let's simplify. So for this first one, take note that 2y squared is the same as 2 squared, which is 4, and I squared, which is negative 1, so we have there minus 4. Then let's just multiply the one in the middle, so that's 2 times 2, 4 times 3, negative 12i. And then for the last one, we have here negative 3 squared, that's just 9. And let's simplify. Combine the real part, negative 4 and 9, so that would be 9 minus 4, 5, minus 12i. Okay, so that's for the first 5 items. Let's go to the sixth one. So we have here 3 plus 4i all over 2 minus I. Okay, so again, just to recall, the goal is to be able to write the given expression in terms of real plus imaginary, or segregate them. So in this case, the key is to recall that I is equal to square root of negative 1. And what do we know when we see radicals? You can multiply the positive version of this one. Because if we multiply the positive or the sum version of this one, say multiply 2 plus I here, or actually let's do it abstract. So we have a minus b times a plus b. We know that when we multiply this one, it becomes a squared minus b squared. So the square root of negative 1 will become square. We can remove the imaginary part. So let's multiply out here 2 plus I and 2 plus I. And then this one will be equal to, for the denominator, again, when you multiply these two, what you do is you square this one minus the square of I squared, which is just negative 1, if you recall earlier. So this one just simplifies to 4 plus 1, or 5. Yep, so we got here 5, and then the numerator, let's just apply FOIL out here. So multiply the first one, we get 6. Multiply the outside one, we get 3i. Multiply the inner ones, we get 8i. Multiply the last one, 4i squared. I squared is again negative 1, so this one is just negative 4. And then let's simplify. basically combine what you can combine. So combine 6 minus 4 out here since they are both real. So we got 2, 3i and 8i out here. When we combine it again, just like adding coefficients, we get plus 11i all over 5. And then just to be precise about it, we can even segregate this one into 2 over 5 plus 11 over 5i, just so you can see that the real part are both segregated. So this one is the answer for this problem. Okay, finally, our last item for this one. So we have here square root of negative 9 plus square root of 8 all over square root of negative 1. Okay, so the key here is we can view it, this one as I, and then this one we can view it as square root of 9 times square root of negative 1, which is 3i. So we convert this one into 3i, and then take note that square root of 8 is equal to square root of 4 times square root of 2, which is equal to 2 square root of 2 plus 2 square root of 2. Okay. And then from here, what we can do is, well, you can do plenty. You can split this up. That could be 1. Or you can multiply something that can remove this radical out here. So at first glance, you might think, oh, I will multiply I. Because when you multiply I, this becomes I squared, which is negative 1. So you can eliminate the denominator. But a more advanced trick here is to multiply negative I. Because when you multiply negative I, this 1 becomes negative I squared, or simply just 1. So we can disregard the denominator already, since it will just be equal to 1. So we'll be left with the numerator, and so we'll have here 3i times negative I. So I can here just distribute this one out here and out here. So we'll have negative 3i squared minus 2 square root of 2i. And then just take note that I squared is equal to negative 1. But we have another negative out here. So negative times negative 1 becomes positive, and we'll be left with 3 minus 2 square root of 2i. And that's the answer for this problem. Yep, so that basically ends the complex numbers series, or complex numbers part, and the series of this one, algebra you need to know before going to college. So again, we learned simplifying expressions, factoring polynomials, rational expressions and complex fractions, rational exponents and radicals, and then complex numbers. So I hope you were able to get a good feel of what algebra, at the very least, you need to be able to master upon entering college. So on the next videos, we'll probably do more complicated stuff that you still need to know before going to college, like equations, functions, polynomials, rational stuff. Yeah, basically that. So yeah, if you have any questions or concerns, just feel free to comment that one down below. Any criticism, constructive ones, would be really helpful. And besides that, have a nice day.